Hey there, today we're going to be looking at partial derivatives. And what a partial derivative is it's when you derive one variable of a multivariable function and the other variables are considered to be constants. So let's do an example to sort of understand what this really means. So let's say I had this function f, that's a function of x and y, and it's equal to x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. So the first little part of the work we're going to be looking at is we're going to be doing the partial derivative of x. So what I'm going to be doing is I'm going to be deriving all the different elements of f that have an x, and the rest are going to be constant. So the elements of f that have an x are x squared minus 3xy minus 4x. So the derivatives of all those different elements will give you 2x minus 3y minus 4. And you can do the exact same thing for as a function of y. So if I do the partial derivative of y, of f, I'll be getting negative 3x plus 4y plus 5. And those are the first order partial derivatives. I can also do second order partial derivatives, similarly to in Cal 1 you do the second derivatives. So if I do the second order partial derivative of x, pretty much what that means is I'm going to be deriving my partial derivative, my first order partial derivative of x a second time as a function of x. So the only element that has an x and f in my first order partial derivative is 2x. That'll become 2. Same thing for f of y. If I derive this again as a function of y, I'll get 4 because of the 4y. And I can also mix up the variables. So let's say for this one right here, f of xy, I pretty much derive my f of x as a function of y. So I'll be left with negative 3y, and if I derive that, I'll get negative 3. Same thing for if I derive f of y as a function of x. So if I have negative 3x plus 4y plus 5, the only thing that has a x in here is a negative 3x. So if I derive negative 3x, I'll get negative 3. And you can see that these are actually identical. And you may be wondering like, oh, is that just a coincidence? But no, it's actually a theorem called Clairaut's theorem, which says that these different partial derivatives will give you the same answer. Next, we're going to be looking at the second part of this little video, is we're going to be looking at the chain rule. And first we're going to be looking at the chain rule for two variables. So the chain rule for two variables is pretty much the same thing as in Cal 1, but now we're just going to be, instead of just doing simple derivatives, we're going to be doing partial derivatives. So let's say I had this function f that's a function of x and y, and its equation is sine of x over 1 plus y. So let's say I'm going to be doing a partial derivative of f as a function of x. So like in Cal 1, you have to do your normal chain rule. So I'm going to be doing the derivative of the outside. The outside function is sine. So the derivative of sine is cos, and then the inside won't change. But now I'm going to be multiplying this first derivative by the derivative of the inside function, which is x over 1 plus y, which is just going to be 1 over 1 plus y. And then that is your partial derivative as a function of x. It's a similar idea for the partial derivative as a function of y, but for the purpose of this video, this example should give you the idea enough of what you need to do for a two-variable chain rule. Next, we're going to be moving on to three-variable chain rule, where this is where it can get tricky very, very quickly. So let's say I had this function z that's a function of x and y, and x and y are a function of u and v. So you see we have multi-variables right here. We have more than just two. Because for 2, it would just stop at z, x, y, and then you wouldn't have these bottom ones, but now you have these bottom ones. So whenever you're doing your partial derivatives, you're generally going to be trying to get the simplest form as your answer, and the simplest form is your u and v's. So you're always going to be deriving your partial derivative as a function of u and v, so your lowest variables. So in this case, if I derive the partial derivative of u, you see how like I'm going to be getting zxu and then zyu. So that's what I'm going to be doing. I'm going to be doing the partial derivative of x, and then u of x, and then z of y, and then y of u. And then that's what I'm going to be getting right here. And it's the same thing for v. So I have zxv and then zyv. So partial derivative like this, and then like that. So that's why you get partial derivative of x of z, and then v of x, and then like this and like this. So partial derivative of y of z, and then v of y. And then that's the main idea for these, just theoretical, what the equation should be when you're doing partial derivatives for a chain rule of three variables. So let's get into an example to sort of work this out, because just these equations are just like, okay, but the problem is where you really learn. So let's say this function right here, z, that's a function of x and y. And then x and y are a function of u and v. So it's the same idea as what we did right here. And u is equal to 3, and x is equal to 3u plus 2v, and y is equal to 4u minus v. So I just rewrote the equations I had right here down here. So that's what I'm going to be doing. So the partial derivative of x of z, well, I'm just going to be deriving this first part as a function of x. So I'll get 6x minus 2y. And if I derive x as a function of u, I'll be getting 3. Same thing for y. If I derive my z as a function of y, I'll be getting negative 2x plus 2. And if I derive my my y as a function of u, I'll just get 4. And then I can multiply everything out and I'll get this equation. If I group the common terms together, I'll get 10x plus 2y. But we can't forget that x is a function of u and v, and then y is a function of u and v, so we can plug in these given equations that we gave in our problem, and then we can just write everything out, and then that's our simplify our answer, and that is the partial derivative of u of z. That's the answer for that. And then now we have the same idea for the partial derivative of v of z. So like we had before, you got to derive partial derivative of x of z and then v of x, y of z, and then v of y. So these, we had these in our first part for the partial derivative of u. These won't change. It's just the second partial derivatives will change, because instead of deriving u, you're going to be deriving v. So what we had initially is we had v. Well, if we're deriving x of v, we'll get 2, and if we derive y of v, we'll get negative 1. So that's what we have right here. We're going to be having the 2, and we're going to be having the negative 1. And then once again, if you multiply everything out, group terms, plug in x, y, you get this big equation, and if you simplify it all, you get this. So the partial derivative of v of z is net 24u plus 34v. And that is the main idea for first order chain rules of 3 variables.